Now to start today, we're going to look at this diagram. We're going to try to find a value for x and y in the form of a complex number, but we're going to try to get it in terms of theta. So what we need to do is we have to get a value of x in terms of theta and a value of y in terms of theta. So this is our y value, this is our x value. We'll just fill these in, y and x. Let's see, we're working on two right-angled triangles. So right now what you should do is go ahead and try to figure out values for x and y. If we try to find a value for x, we won't use the y, we'll use the radius, and we've got this angle theta. So towards that theta, x is the adjacent side over the hypotenuse, so that sounds like cosine. So cosine of theta is x over r, so that will mean x is equal to r cosine theta. Good. Let's try y. Y would be the opposite over the hypotenuse, so that is sine. So that is y over r. So in other words, y is equal to r sine theta. Now the next thing we want to do is we want to write z in terms of these values. So the one thing I want to do before I start that is I want to look at r. In terms of this complex number z equals x plus iy, r is just the modulus of z, or the magnitude of the vector that's represented there. So now if I can use that for r, see x is r cosine theta, we're going to put in the modulus of z instead, modulus of z cosine theta, plus I times y. Y is r sine theta, so I'm going to put in the modulus of z sine theta. And we're going to factor out the modulus of z. And what do we have left? We have cosine theta plus I sine theta. Now, of course, mathematicians are lazy by nature, so that's way too much for them to write. So instead, what they write is z is equal to the magnitude of z, the modulus of z, times, and they shorten this down. They take the c for cosine, they take the I for I, and they take s for sine. And theta is the angle. And that's what we call cis theta. So any complex number can be written as the modulus of that complex number times the cis of theta, which is really cosine theta plus I sine theta.
So we've seen two forms that a complex number can take, and this summarizes it right here. Any complex number z has Cartesian form, z equals x plus yi, which is what we started with, or what we call the polar form, the cis theta form. Z is equal to the modulus of z cis theta. And just a reminder that cis theta is cosine theta plus I sine theta. There's a third form of a complex number as well. This third form was developed by Eulor. You see his picture here. He lived from 1707 to 1783. His form works with cis theta, and it is that cis theta is actually equal to E, which is Euler's number, to the I theta. Now, there is a proof for this. We're not quite ready for it yet. We have to take some more advanced mathematics before we do it, but we might see it a year from now. But for now, I'll just show it to you quickly, and you can ooh and ah at it. Ooh! Ah! The next thing we should look at is the conjugate of a complex number. Just a reminder, if this is our complex number, z equals x plus iy, the conjugate would be down here, z equals, or the conjugate of z is equal to x minus iy. In this diagram, they've used a line above the z to represent the conjugate. We always use z with an asterisk. From before, we showed that x was equal to the modulus of z cosine theta, and y was the modulus of z sine theta. Then the conjugate of z, which is x minus iy, would be the modulus of z cosine theta minus I times the modulus of z sine theta. So let's factor out the z. That would give us cosine theta minus I sine theta. Now that is not cis. That is not cis theta at all. Now you'll notice also that the angle we would actually be working with would be down here, this minus theta. So a couple of things we can do in order to get the minus theta in there. We also want it to be a plus sign. Well, we notice that because of the cast rule, just a reminder, cast, cosine theta is actually equal to cosine of negative theta. So that's one thing we can use. And because of the cast rule, we know that sine theta is actually equal to negative sine of negative theta. And what I'm going to do is I'm going to plug these guys back into here. So that makes the conjugate equal to the modulus of z times, so we're going to replace cosine theta with cosine of negative theta, minus I times, and I'm going to replace sine theta with negative sine of negative theta. A whole lot of brackets. 1, 2, and I need one more. So if we simplify that, I can make that a square bracket just so it's easier to stand out. That becomes cosine of negative theta, and that becomes now plus I sine of also negative theta. Well, that now is a cis. We can write that as the modulus of z times cis of negative theta. And that's our conjugate. So the conjugate is the modulus of z cis negative theta. Our first example is to convert each of the two complex numbers that were shown here, and we're going to take them and convert them into polar into Euler form for each complex number. So our first one we're going to do is we're going to try to convert 1 plus I. So in order to convert into polar and Euler form, both forms require the modulus of z, and both forms require theta. So how do we find these? Let's just remember that the modulus of z is the root of x squared plus y squared. That would be where z is in the form x plus yi. And theta we can find by doing the tangent of theta is equal to y over x. So let's get to it on this first one. So the modulus of z would be 1 plus 1 squared plus 1 squared and the square root of that. So let's find theta. Theta would be, the tangent of theta would be 1 over 1, or 1. Now if we were to graph 1 plus I, it's actually in the first quadrant, right there at 1, 1. So we're talking about the first quadrant, and this is theta. So we know by our special triangles that theta would be 45 degrees, or pi over 4. Remember, for complex numbers, we're looking at theta always being between negative pi and pi. Alright, so that means radians. So our answer then, z, could be written as root 2 cis of pi over 4, or root 2 in Euler form, e to the I pi over 4. So I shrunk down part A so that we can now do part B. So right now, see if you can follow the steps that I followed in part A, and see if you can figure out a solution for part B for both polar and Euler form. So let's check your answer. First, let's find the modulus of z. It would be the square root of 1 squared plus negative root 3 squared. That works out to be root 10. How about the angle? Tangent of theta would be negative root 3 over 1, so negative root 3. So let's do some figuring here. First of all, what quadrant is this in? This is in 1 down root 3, so it's down here somewhere. 1 negative root 3. So it's in the fourth quadrant. So by the cast rule, tangent is negative. And so if we check our special triangles, we've got a 60 degrees, 2, root 3, and 1. So we're looking at tangent of 60, or pi over 3. So now because it's in that fourth quadrant, we're actually going to use theta equals negative pi over 3. Again, remember, theta is going to be between negative pi and pi. So how can we write z? Z could be written as root 10 cis of negative pi over 3, or it could be written as root 10 e to the I to the negative I pi over 3. I know, bad joke. But you know, Darth Vader has always had a special place in my heart.
I am your father.
It still tears me up. Okay. Alright, back to what we're really supposed to be doing here. So what we want to look at is what would happen if we were to take two complex numbers in polar form. So let's take cis theta and cis alpha. And what would happen if we multiplied them together? Well, let's expand it. Cis theta, remember, is really cosine of theta plus I sine theta. And cis alpha would then be cosine of alpha plus I sine alpha. So let's expand them out. You knew it was coming. Cosine theta times cosine alpha plus I sine alpha cosine theta plus I sine theta cosine alpha, and the last part, I squared sine theta sine alpha. Oh, lot. What can we simplify this? Well, we know the I squared would be negative 1, so we're going to get the real components together. So the real component would be cosine theta cosine alpha, and that would become a minus sine theta sine alpha. Let's do the imaginary components. So plus I, and let's factor it out, sine alpha cosine theta plus sine theta cosine alpha. Alright, so let's start by looking at the real component. Cosine theta cosine alpha minus sine theta sine alpha. Does that look familiar? Certainly does. Should be a compound angle formula. Which one is it? Well, let's see. Cosines first, subtract the sines. That would be the cosine of theta, and the opposite sign always for cosine, plus alpha. And how about in the imaginary portion? We got sine alpha cosine theta cosine alpha. So they alternate, but sine and cosine, it's an addition, and sine of theta plus alpha. So you can see we get the same angle, and it is a cis. It's got the addition. So this becomes the cis of theta plus alpha. So if we multiply two together, the cis of theta times the cis of alpha, we do get the cis of the addition of the two angles. Now, there are actually three different rules for the cis, or for polar form of complex numbers. And we just did the first one, which is if you multiply two complex numbers together in polar form, all you do is you get the same complex number, except for it's the addition of the angles. Similarly, if you divide, it becomes subtraction. Does that remind you of anything? Sounds like exponent laws. And the third one looks at taking the angle and adding on a k times 2 pi, so multiples of 2 pi. Now remember, 2 pi is the period of sine and cosine. So it does make sense that it does work out to be just cis of theta. So you can simplify large angles down to be just cis of theta. The proof of these is left up to you. I will be kind enough to show you, however, the proof for Euler's form. If I took e to the I theta and were to multiply it by e to the I alpha, well, these are just exponents. So with the exponents, I can just add them together. E to the I theta plus I alpha, which gives me e, if I factor out the I, theta plus alpha. Isn't that nice? Our last example is dealing with trying to simplify an expression in polar form and trying to write it in complex form. Now, as a reminder, complex form is z equals x plus yi. So we're looking at to get it down to that form. Now, right now, if we take a look at part A, we've got 2 cis pi over 12 cis pi over 6. Now to simplify this, we're going to take the modulus, which is 2. It's not multiplying by anything, so it's not going to change. And we're multiplying two polar forms. So we need to add the two angles together. So it's a cis of pi over 12 plus pi over 6. Now, you could, of course, skip this step and go right down to the answer, which is then 2 cis, that would be 2 pi over 12, so 3 pi over 12, or pi over 4. Now, we can't leave it there. That's still polar form. What we need to do is then evaluate it. So that's going to be 2 times the cosine of pi over 4 plus I sine of pi over 4. So that's going to be 2 times cosine of pi over 4 is 1 over root 2 plus 2 times I, and again sine of pi over 4, 1 over root 2. Can we simplify that more? We certainly can. That would be 2 over root 2 plus I 2 over root 2. Now if we rationalize those, we would get multiplied by root 2 over root 2. Root 2 is on the bottom, we make it 2, cancels off with that 2, and we just get a root 2 plus I root 2. There it is in complex form. Let's try the second one. The second one is a division. So we can now divide these two. First, root 32 divided by root 2 is root 16. We then would subtract the angles. So that's a cis of pi over 8. Subtract negative 7 pi over 8 is plus 7 pi over 8. So you can see that works out to be a pi. So root 16 cis of pi. Root 16 is of course 4 times the cosine of pi plus I sine pi. which works out to be 4 times cosine of pi. Starts at 1, goes down to -1, so that's times -1, plus 4 times I sine of pi is 0. So our answer here is -4. Okay, we're ready for the last one. Cis of -37 pi. So this is using that last one in which we can subtract or add on, in this case because we're at negative, we're going to subtract or add on multiples of 2 pi. So what I can do, and it would still be the same. So I can take this and add on, for instance, 38 pi. That would be 19 times 2. Right? So I'm going around 2 times, and that would work out to be the cis of pi, which is the cosine of pi plus I sine pi. And that works out to be, cosine of pi is -1, and that's 0, so it's just -1. Alright, class is over. Everybody out. Come on. Get out, keep going. Get out, get out, get out, get out. That's better.
This was a triumph. I'm making a note here, huge success. It's hard to overstate my satisfaction.